Hello, everybody, and welcome to this special episode from BLS, live from Prisma headquarters in Berlin. With me is Dominic Petrick. Dominic, hello, welcome to the show.
Hello, thank you for having me.
It's awesome. So, just for the records, it's BLS Beam and live stream, but we're not really live streaming. I'm recording this, and it's going to be on YouTube at some point in the near future. Today we have a special episode of Show and Tell where Dominic is going to tell us something about how Prisma works behind the scenes. So basically all the stuff that we as developers don't have to worry about. But before that, Dom, can you maybe tell a bit about what your role is at Prisma and something about yourself if you like?
Sure. So I am the tech lead of the client team, or what we call the client team. Prisma has three teams now, actually. So the client team, the migration team, and what we call the scale team, or that build the commercial product. And I'm the tech lead of the client, which is the open source component that you use to query databases. The migration team, on the other hand, is building the tooling for you to make migrating data, for example.
And then the third team is working on things like the cloud offering.
Yeah, that we may talk about. Let's see.
Yeah.
So yes, exactly.
Good. Awesome. So I think one of the main benefits, actually why I like Prisma is that it takes away a lot of the things that I would normally do myself. So it's abstraction above databases, I guess, is the way to say it, a way to view it. And then for me, the relevant parts are obviously the schema file, which is like schema.prisma, where you define the whole desired state of your database. And then one of the things I kind of need to know is that it generates a Prisma client on TypeScript. It does that in Node modules directory. And then from there on, it magically works its way down to the database where it gets stored. And this is all, for me, it's a black box. It's a good black box. I'm happy that it exists. And I guess today's goal is to look at like, now what actually happens with this?
Yeah.
So
let's do that.
Good. And I think it's probably good if you share the screen. And if we can look, it's already shared actually. Just need
I have some repositories here. Right. So Bram already mentioned it. It's so Prisma has an interesting structure for an ORM. Usually, if you look at something like Active Record or Type ORM, it's basically a library that you bind your program, right? And it's written in the language that you write in. So Type ORM is written in JavaScript or TypeScript.
Yeah.
Prisma, on the other hand, has two components to it that make it actually work. And let's say, the layer that makes it nice, that decides how to expose the API, is the TypeScript. And that is binding to something called an engine, and that is written in Rust for us. Actually, all our engines are written in Rust. And before Prisma 3, we had a binary running for you in the background called a sidecar. And that was basically an HTTP server that accepted requests and that exposed a specific API and that the TypeScript client binds to. And now with Prisma 3, we have something called Node API, which is basically loading or compiling the Rust code to a library and binding it directly into your Node process. So it's a slightly different thing now. So we can talk about that. It's very interesting. As well. So let's maybe start with the top level repositories that you may know or may not know. Yeah. So the one that you do know most likely is the Prisma repo, and this is where the engine code does not live. So what you have here is the client, and we use it a lot for issues. So thank you for filing all these issues. We have a bunch of them, and we're actively working on making it better. And then you have the Prisma engines repository, and that's the one where you actually have all the Rust code for all the engines. So let's dive into the code a little. So I have this repository open here.
Could you increase the font a bit, please?
Oh yeah, sure, of course. Let's do like this. That's better.
Yeah, or if you can do one notch up, I think it's going to be perfect.
Right, let's do this.
Yeah, awesome.
Perfect. Awesome. So you have the repo right here, and you can instantly see the So we have 3 engines that we're actively developing. The first one is a query engine. That is the one we're talking about the most here. And then we have the migration engine. And we have a bunch of libs that we will talk about. These are like shared things that also include the data model parser. So you mentioned the Prisma schema file. Well, the Prisma schema file is pretty much the anchor of the entire Prisma ecosystem. It is extremely fundamental to everything we do. So let's maybe dig up an example. This is the one we usually use for development of the engines. We have like one sample thing that is just a SQLite database. And everybody that uses Prisma has to, in some form, modify and come up with a Prisma schema file. And as you mentioned, this is where the magic mapping happens, right? Like somehow we allow you to define a model album, and then you suddenly have an API call, a typed API call that says create an album, update an album, read an album. So how do we get there? Maybe let's first talk about the Prisma schema parser, right? So if you ever wondered how that is implemented, well, it is of course a parser, so it pretty much follows the same rules, but where you can actually find that code if you're interested in how it works, it's in the libs data model. So we have throughout Prisma we have a notion of connectors that we use a lot. So every database exposes different characteristics, has different capabilities, and this is also shown in the schema file, right? So if you add a JSON field to an SQLite database, it won't work. It will complain that you cannot have a JSON field, and this is defined over capabilities. So you have these connectors that say what these databases are capable of. So the newest one is the MongoDB connector, and then we have all the SQL connectors for all the current SQL connectors that we support. So if you look at SQLite, it says capabilities. Well, you have a bunch of those, right?
Yeah.
Nothing of that is really surprising. So you can update the ID. Not every database can do that. It doesn't have JSON, for example.
It doesn't have enum.
It doesn't have enum, correct? Yes. Yeah. And if you look at Postgres, on the other hand, there's a bunch of native types. It has a much longer list of capabilities, right, that you can do. So even insensitive filtering right here, or of course the JSON type and the enum type, the love use.
Yeah.
Right. So every one of those has capabilities, and that influences what you can do in the schema. And that is, yeah.
So in essence, that means that if I change in my Prisma schema, I change from Postgres to SQLite, that the client that gets generated is also different based on its capabilities.
Exactly. Yes. Yeah. This is not only used in the parsing of the schema, but it is also used throughout the API to generate the API. Yeah. We'll see that in a second when we go over how the high level, how the glue actually works, right? If you look at Prisma, because that is very, very interesting. Okay, cool. So if you go, this is an active area of development. So it basically evolved from Prisma 2, the very early days, to be as flexible as possible. But we're trying to, because we learned a lot in this time, we're trying to clamp down the code and make it nicer, to make it like an easy pipeline that everybody can follow if they just read the code and click through it. At the moment, it's a little bit confusing. So I won't go into much detail. Mm-hmm. But I will talk about the high-level concepts that are at play, and the first one is the syntax, right? The syntax definition. And Rust has a lot of really awesome parsing libraries that you can use to make it happen, because the Rust community in general is really, really great at just coming up with awesome tools for all these low-level jobs. Like with parsers that are super flexible that you can just include in your code and start defining something that works great. And one of those is pest. And if you check out the pest file that's in the parser, it actually defines the schema in a fairly easy to read syntax, right? So you have the schema, for example, and it can include model declarations, enum declarations, and a generator block, for example. This is the one you typically know. So it basically directly reflects on what you type. You say data source, my data source, with all the definitions. Same with models. So let's check out the model definition, right? A model can be a comment. It must have the model keyword, and it has to be a block open, and then you can have a bunch of field declarations inside of it. So you can basically go through the syntax tree and see how the Prisma schema is built as a valid syntax, right?
Right.
And this
So
generates code.
in essence, you have a schema for the schema file.
Yes, we have a schema for the schema
This
file.
is pretty meta. This looks super interesting.
And what happens here? This generates code. Let's go to a model. Right. So let me quickly find the correct place. Right. For example, where's the exact? So the parse schema is basically the root, right, of where you would start parsing something, and you basically just get a string. So at the moment, the Prisma schema is basically one big string that the client hands to the engines to do something. So the client itself doesn't parse. It is all the Rust code that does all the heavy lifting, which is also the parsing. An interesting side note here, we are currently exploring how to compile this to WASM. Because at the moment, it doesn't really make much sense to always invoke an engine, always to have a binary present to do this kind of parsing, right? In some environments, you cannot have the binary, or it's hard to do, like in a serverless function, for example, it is very tedious. Yeah. So a WASM module would be much easier to just include. You get the parsing, and you have a nice binding to the Prisma core modules like the schema parsing.
Got it. Yeah, I realized. So when I started with Prisma 2, I was running on Alpine Linux, and this was one of the examples that didn't work. You fixed it fast enough. The team was pretty fast in doing it, but it kind of shows the point you want to make. Like you still depend on some OS build thing. Yeah.
Yeah, I'm also responsible for all of this, so I was likely the one that fixed it. So it is incredibly complicated to distribute binaries, also because of OpenSSL, right? As soon as you bind to a specific version family of OpenSSL, you have to compile a whole set of other binaries. So it is very complicated, but we're trying our best for the distributions. We recently added ARM. We're trying.
Awesome.
Okay, back to the schema parsing, and here you can see something called rules, and this is generated code. Like this magically appears for us when we use this parsing library, right? And so we can basically go through all the definitions and say, hey, please parse a model now, please parse an enum now, and this generates a basic AST, but that AST is basically only conforming to the syntax that you used, which is structural, but not semantically validated, right? So you still can have, for example, a JSON field, right? And the pest syntax would not prohibit you from typing a JSON field. It is simply a field definition for it. So semantic validation happens in a step afterwards. So so this is basically the parser. This is the AST component, which is the structural part of AST building, of the schema AST building. And then you have something called the data model, and that thing is what we really use internally, right? So this is the validated AST, and we do something called lift the AST to a data model. And that part is under heavy development right now. And what falls out of this is basically data model, right? And this is basically what you want. This is the validated AST that we work with, and that is also responsible for generating your API.
So this
So
is
if
like first go is basically syntax, and if that's all
yeah,
correct, it goes check if it actually makes sense what your syntax defines.
exactly.
Yeah.
Yes. So basically, let me see if I can quickly find that, but I don't think I like super. I'm not entirely in this code all the time. This is my awesome colleagues from the migration team are mostly maintaining this part. So for example, here you have a bunch of validators. So we for example prohibit certain names that are keywords usually in TypeScript, right? So
Mm.
you cannot use the type word, right? So you need to validate all of this. So all the
Yeah.
semantic validation happens in the transform later, AST to DM. And you can also go backwards. But okay, so that's basically the very high level of the schema part, right?
Yeah.
So if you're interested, this is the very rough overview. And if you want to dive into the code, please feel free. This is very interesting stuff.
Awesome. Yeah, I'm definitely interested in checking it out. I'm actually, it's one of the reasons I'm interested in learning Rust is so that I can better understand how Prisma works. So yeah, so the schema gets parsed, and actually,
Mm-hmm.
so any tool, as you said, the client generation, but then also maybe the language server that's used in the IDEs get powered by these parsers.
Exactly.
Yeah, yeah,
Yeah. So you see Prisma FMT is more like is the reformatting tool and the the language server, like part of the language server. The language server itself is written in TypeScript somewhere else, but
hmm
this is Prisma FMT would be where you look at that
yeah,
powers that, and that is reusing, of course, the data.
yeah. Awesome. Yeah, great. And then we
Okay.
have the data model. So this is basically, as I imagine, a data structure in Rust that can be
Yes.
used to do actually interesting stuff with it. Like, I mean, defining the model is one thing, but it's just a desired state, and now we need to actually do
Exactly.
something with it.
Okay, so here we can basically go over to how the API works. Okay, so how do you go from defining a model to having suddenly a nice API to work
Yeah.
with? And that is on top, it's type safe, right? So you get actually compile errors if you do something wrong, even like fairly clever stuff like, oh, I defined a default on a field, and suddenly I don't have to provide it anymore in the create input, right? And if I change my schema to not have a default anymore, you suddenly need to provide it to make it happen. So there's like clever decisions going on in the back, and how does it work? Well, for that we go into the query engine, and the query engine itself is fairly similarly structured to most of the other engines. So we have a test kit that is all our integration tests. So Prisma follows we have very little unit tests because it doesn't make sense. Most of the components only can be tested in like for their semantic correctness in tandem with each other, right?
Right.
So what we do is we have extensive, like 15,000 or 18,000 tests that run against the API.
Wow.
And this is basically this test kit here. Then we have the connectors, which define the interface, how to talk to databases. We have the core that is the actual heavy lifting, like this is the meat of the query engine. Then the query engine package itself is the binary server. So this is basically just spinning up the server, binding all the correct components from the core, and packaging it into a binary. And the Node API one is building the library. And the request handlers are just common stuff for those two. Okay, so what we want to do is maybe dive a little bit what actually happens under the hood. Like what happens if you type out a query in the TypeScript client or in any client really, and what happens under the hood? Well, you have this nice API. You say, for example, prisma.user.create, and what happens underneath is it gets translated to GraphQL. So GraphQL is a implementation detail at the moment of Prisma. Some people found it. Some people are using it actually to do stuff. It's not really documented. It's not really encouraged to use, but we use it heavily in development, right? So let me quickly show you what that means. So Let me see if this 4466, of course.
Still 4466. This brings back memories.
Yes.
There
So
you go.
there's actually a playground, right? You cannot find this on production binaries because you have to enable it first. But the team that works on the query engine doesn't think in client queries because the client queries are just a wrapper around the GraphQL that gets sent under the hood to the server. And this has a lot of historical reasons that are maybe interesting to see. So Prisma started out as GraphQL way back
Yeah.
in the day, and that was a GraphQL backend as a service. Then Prisma 1 came out of that, which was a GraphQL binding to your databases that you ran yourself. It's was more of an API proxy. And Prisma 2 basically eliminated the GraphQL on the very top level. It didn't really make any opinions about if you should use GraphQL or not, but internally we still use GraphQL. And the schema that we will talk about is still partially translatable to GraphQL, which is why you can have a playground against the engine to talk to.
Interesting.
Right.
So it's like a superset, and like you extend GraphQL.
So for example, we needed unions before GraphQL had unions.
Got it. Yeah.
So we built that ourselves. It's different from what GraphQL in the end uses now. With tagged unions, I believe, is what they use. And we have certain constraints on objects. Let's say you need to provide at least one field of these optional fields. So it is a superset of GraphQL, really, and in some ways it differs. Anyways, so you can actually like have a schema, right, that is present on this. This is a heuristical approach to rendering the internal schema that we expose to the client that I will show later to a GraphQL schema. And you have a lot of operations here that we generate for you, and this is how we talk to the engine. This is what the TypeScript client in the end does. So this is the first step. This is the first puzzle piece, and the second puzzle piece is how you actually generate the code that generates these these queries, right? And that is called, so we have something called the data model meta format, DMMF. You may have heard about that or heard it name dropped sometimes. That was also never.
Yeah, I saw it when I started looking at opening up the Prisma file myself, because I wanted to do some, I don't know what I wanted to do, but I want to do fancy stuff. And the DMMF is, at least in the TypeScript library that I use, it's a strongly typed way to traverse the whole structure. And
pretty much.
So looking at the DMMF, and this is basically the representation of the Prisma file in JSON format, the way I can understand it.
It's even better than that. It's much more. So we'll dive into that. So let's grab that.
Yeah.
And let's take a look of what is actually included here. So it has three main components, which is data model, schema, and mappings. The data model is what you just said, more or less a representation of the ASD as JSON. If you have a client that needs some special, like that just needs to dig into the model AST a little bit, that can basically, you can generate a client just using this information, but it won't be as nice or as powerful, because what you get from the other key, which is schema, that is very close to a GraphQL schema, if you have understanding of that, and this describes the API actually. So let's check it out. It has input objects, it had output objects, and it has enum types. And if you know GraphQL, this is very close to how you would define GraphQL objects. So it was definitely inspired by that, but it's not one-to-one GraphQL.
Right.
So let's check out the output objects, because here we have the root types that you also have in GraphQL. So you have a query and you have a mutation. And here, what the core does basically, it takes your schema file. It has the knowledge of all the models, of all the fields, of all the relations, and can generate an API based on that. So if you have, let's say, an ID field and a name field on a user, it knows that it can create an input type for a create operation that needs you to provide an ID, and it needs you to provide a name. If the name is optional, it knows that it can be nullable, right? That you don't have to provide it.
Right.
And this is all happening over these definitions. So if you have a query, you have find first album, then you have an argument or a list of arguments that says where, order by, cursor, take, skip, all the arguments that you know from the API.
Right.
Here, basically packaged as GraphQL arguments. But if you look at your client queries, then you can imagine that it pretty much maps to a GraphQL query, a client query that you can write.
Yeah.
And this is basically a flat graph that points to itself, right? So if you look at the where type, it has another type that you can input, which is an album where input. And if you go and look for that, let's do it like this. Then you can find that object that you need to input, right? And so you can go through the entire tree until you come to the leaves, which are usually scalar types, right?
Mm-hmm.
And build a client typing based on that, so that this entire JSON blob gets taken by the TypeScript compiler and turned into types for you. And if, like, simplistically, it just says interface album where input and just lists the fields with some constraints on it, right? And that's it. You already get the niceties by just building from the very root down to the leaves this tree as an API. And so the query engine builds that and basically says, this is how a valid query looks like that you can fire against Prisma. And of course, we don't trust the clients. There will be validations, right, of every query that comes in. And that is also using exactly this structure to validate, because it's just a tree. So you can go through the query, go through the tree, validate everything against what we defined here, and throw an error if it's invalid. But the real power is the compile time safety that you get from this. Of course, you can argue, well, what about languages that are not as powerful as TypeScript, right? So we're currently building a Go client on the side, and that has completely different semantics, like completely different characteristics on how they handle types. So TypeScript is more or less a unicorn, because it allows pretty insane constructs and pretty powerful constructs with types only. So we are exploring how this is applicable to other areas as well. But TypeScript really brings out the power of this schema and this approach. So you can imagine that. But you can imagine, yeah, sorry.
But if I understand correctly, so the basically the runtime validation is very similar to what GraphQL gives you then. So if you have a schema that you validate, and if you try to do something, you can, even before it gets to the point where it executes, it will already be dismissed.
Yeah, and it's not like GraphQL invented this, right? It's fairly similar to how most incoming ASTs would be validated, but it is close to GraphQL in semantics for sure. However, as I said, there are additional constraints that you can put on it that make it a bit better than what GraphQL would give us at the moment. So if you want to define max or min numbers, right, on fields right here.
Yeah.
Just one example.
Yeah. Awesome. All
right. So maybe let's dive a little bit into the code where this happens, where this is built. If you want to look at what we allow, how that looks like, then the right place to look is the core and the schema and schema builder. So schema is basically just the types, the building blocks that we use to build it. That is not the actual schema. So if you look at output types, for example, you just have like your building blocks. What is an output type, right? It can be an enum, list, object, or scalar. And the same goes for input types. What is an input type? Well, an input object type has an identifier constraints field. So you find all the models basically that make up the schema right here. But the interesting magic happens in the schema builder. Right, so let's go here and let's go here. There's a lengthy explanation on the top, and here we have the root of the builder. Let's scroll down a little here. Build. That is the function that you're looking for. that takes something that is called the internal data model. I won't go into detail. You can imagine it's a thin layer on top of the data model that we talked about. Mm-hmm. To make it a bit nicer to use for the application, for the things that the query engine needs, like traversal of relation fields. For example, you want to say, hey, give me for this relation field all the related fields. Yeah, for example, that because you can have multiple, and to traverse the tree easily in your data model. So we built some decorators around it. You could imagine. So don't get hung up on that. The mode is legacy, so for some time we supported Prisma 1 schema syntax as well, so ignore that as well. And then some stuff like you would expect. The preview features that we built influence the building, and of course the capabilities that the connector has, right? And if you want to include raw queries or not. And from here you go ahead, and the interesting part happens in the query and mutation type that you build, the root types, right? So you can read this as read queries and write queries. Mm-hmm. So let's go into read queries. What happens here? Well, we basically say take all the models, and now we go ahead and build the operations for the schema. So you saw the find first album before. So what happens here is, well, for each of these models, let's go ahead. We build a find first operation. We build an all items operation, so to find many in this case, and we have some aggregation, and we have a group by aggregation, and we have a find unique. You can basically see all the root operations that you're used to defined here. And if you dig into it, let's take the unique find unique. If you dig into it, well, you basically always see you get something like a model with it that defines, hey, I want to build the find unique operation for that specific model. And you go ahead and say arguments. Well, what arguments do I need for where operations? This is all developer defined, right? So we think very hard about the operation. So what users want. Like you have a feature request that says I want an operation that does X, Y, Z, and then we sit down and do a design pass or multiple design passes to find how it fits into the current API. So what we currently do with the arguments, if we can reuse something, if it makes sense to build something new, and then we design these functions first, right? Because the API is king for us. We always start at the top with the design.
Yeah. So API, we say, then you mean the generated clients.
Exactly, because API is basically, we refer to API because the client, the query engine exposes that as an API, basically, right? So, and what the client does is simply bind to that API.
Yeah. So basically, API is seen as me as a developer interacting with Prisma. That's the first and foremost thing.
Yeah, and the cool thing about it is, if you would say, okay, so the find unique operation really needs a different argument or a new argument, right? Then most likely you don't have to do anything on the client side to integrate it, apart from like end-to-end tests and so on, because it is just automatically generated. So it would just appear, and because all these building blocks are already known how they can be rendered, how they work. It will most likely just work. So if you play around with this and add a different argument, you will just see it working, which is super cool, because all the puzzle pieces start falling into place as soon as this end-to-end stuff is really happening. Okay. So usually what the most important part is like naming, for example, right? Like a lot of people, we try to be really diligent in terms of naming, but you get these Java-esque long type names from time to time, and we're trying to figure out how to do that better. But it's basically, you take usually the model name, right? In this case, it's the pluralization. This is not a thing anymore. So you back in the days, if people are still listening to this that used Prisma 1 or GraphQL, we had some really funny reflection errors in the naming of the fields. This is gone with Prisma 2 and now Prisma 3. And we usually have something very structured like find unique and then model name, right? And then you say, okay, we want the where unique argument. So we have two types of selectors in Prisma that are fundamental to how you select data. This is, for one, the unique one, the unique where argument, and the non-unique where argument. And unique is where you specify a unique specifier like a slug or an ID that you have on your model that has @unique or @ID or @unique, right? And that pins exactly one record in the API. And the where is just select how many records will come back, right? Like where name includes test. Yeah, that would return many records. So we have two types, and this one is the where unique argument. And then you say, okay, so what is it? In the end, it's just a field on the query object. Yeah, you have a field called find unique album. And it says the type of that field is an object that has a specific form that gets rendered underneath. Like you can imagine, it's just a list of all the unique fields, for example. And then that's it. That's already it. And this field is nullable. This can return null. Right, and that's about it for like a very simple operation already. And you basically just take all of these little Lego bricks that you have and just put them together like how you want: an object, a field, a type of that field, a type of that object, and build the schema. And that will automatically be represented by generated types in the TypeScript client. So you have this contract going on really between the engine and the TypeScript client based on this type generation, on this what we do right here.
Looks super impressive and super clean, honestly. This is, yeah, definitely impressive feat of engineering, I'd say.
Thank you. We are trying very hard to also evolve that idea because it is pretty good already, but you can always, so you most likely won't get a GitHub issue that tells you, but what about if you do it completely different? This entire approach, right? So we are really trying hard to get like a lot of great people that want to work on this problem field and really try to solve that issue in a nice way. So yeah.
And you're hiring, so if
yes, we are. Yes,
yeah, Prisma's hiring people, so yeah.
You don't have to know even Rust. If I can do a little plug here, you don't have to know Rust. You just have to be a good programmer and have to have the passion for this problem field to solve these kind of issues.
Awesome. And I wait a little bit down. I see the find first field, which is basically doing a where query for multiple, but it just takes the first one.
Exactly.
And
yes.
This looks super similar. And I think at a certain point, if you find the right abstraction, you're inevitably gonna have a very few methods that look very similar. And I think it is also one of the challenges is to not try and abstract this even one further, because you can already squint your eyes and look like, but there's only 5 places where I change it.
Yeah. You know, the next step would be if we really think that this is it, that this is the nicest thing we can do, we can use something like Rust macros. So if you're knowledgeable of Rust, it has a super nice macro system where you could basically write something like a DSL yourself. You could say field, and then basically build a little AST inside that gets translated to Rust code in the background and make it even more ergonomic, but the basic idea would stay the same for sure.
Yeah, and it's often pretty okay to have things like this. It's 15 lines maximum per method, so that's totally justifiable.
Yeah, of course, there's a lot more magic happening in the background, right? So what does it actually entail to build an object type? Well, let's see. Oops, this is the wrong one. We definitely have to go into much detail, especially the write operations. The read operations are not super interesting, but if you just go into an upsert, well, upsert needs a lot of types. So for example, it needs the update and create types, and then it gets really, really hard all of a sudden because you have to do a lot of code in the background, a lot of logic. As I already said, we want to be clever. We want to give you a good DX, and we want you to feel secure when using the API. So if you write a query that compiles, it should give you high confidence that this is actually a valid query and doesn't error at runtime, for example, right? Runtime errors are fine because an error is better than an incorrect query executing. But compile time safety is really what we're after here, and gives you like a ton of safety by just developing.
Yeah. I think
yeah.
most weird questions of people that ask me like, hey, I can't do this in Prisma, was either they used any somewhere in TypeScript, so basically sidetracking the whole type system, or they didn't type it, and then you have like, you need to, for instance, Prisma user where inputs, you type your object, and then all of a sudden it starts complaining like, hey, what you try to do doesn't make sense. And yeah, I really, this confidence is definitely really good, because it's confidence that you don't do something wrong, and it's confidence that if Prisma is okay with it and it works, then it most likely has the effect that you desire. So that's definitely
pretty much that. Yes.
Yeah.
Okay, that was a very high-level overview of how the binding work, how the magic works. Right. So what can we dive into next?
Let's see. So we looked at the parsing schema. We looked at how Prisma client communicates with the query engine. I think there's two things that are interesting. So Prisma migrations, I mean, I guess that's more to do with how Prisma instructs to the database what things should be written, because we've talked about the data itself, like reading, writing queries. But for most databases, in order to do that, you need to prepare tables. And like let's look at SQL in this case, where we need to have a table that needs to be created. I'm curious if you can show a little bit about how that works.
So this is definitely not my area, right? So this is the other team that does that, but they did a lot of like nice work to get it discoverable, to make the code really nice, and to like for you to read the code. It doesn't really take magic. So let's dive into it together. I haven't looked at this code in some time. So it is located in the migration engine. So as much as the introspection engine, right? That is the other workflow that we support. And of course, we generate SQL for you to run. That's our basic approach, right? So of course, you can have an end-to-end workflow with Prisma Migrate, but what we want also to achieve is, because we know data migrations are a hard topic, right? And usually, if you have a migration solution already in your company, let's say even small companies or medium-sized companies, it is usually hard to break into that space, right? Because if you have a DB admin, if you're big enough to have a DB admin, you will most likely not use Prisma to actually execute the migrations, because you have your own procedures and so on. But having SQL already rendered for you that can help you start the process or help in the process, that's already a big value, right? So this is basically what we chose to do. And
And if I understand correctly, because I don't use Prisma Migrate that often, but it does generate the things that it will execute for you and persist it in the repo, right?
So yeah, it's I don't know every little detail here, but high level, Prisma Migrate maintains something that it calls the shadow database. That basically helps you figure out stuff to migrate. It's like an internal meta table that we require, and what the main heavy lifting, because if you just imagine create a table for this model with these fields, that is fairly simple, that is fairly straightforward, right? But the actual hard lifting comes with diffing existing structures, right? Like you want to migrate from a state A to a state B. And this is where the main work of the migration engine comes in. So let's see, let's dive into that. We have a CLI for the migration engine, right? We also have, again, the connector concept. It's found throughout all of Prisma, where you can say, okay, how does a migration connector look like? Let's see if it's defined right here. Yeah. So you need to like provide certain methods like on the interface to make it work. I guess the most interesting ones are diff, right? So this is actually one of the magic functions, right? One of the hard functions. Reset is easy, makes sense because also we use migrate internally for our tests to set them up. These setups are very easy, just drop everything and create tables, but this functionality, of course, needs to be there.
Yeah.
Let's see what else we have here. Yes, a bunch of meta functions that are probably that are used throughout the workflow of determining, hey, how do I get from A to B? Right. So let's see. We have a bunch of. Yes, this is not the one that I'm looking for, actually. Let's see how for example, the Postgres, I like to use Postgres usually, works. So here you can see the word that I mentioned, the shadow database connection. Let me just quickly get an overview of that. So, so they went for a different. So, for example, in the database connector, we have a connector implementation for every single database, and here it looks like the approach was, for example, to choose a flavor, right? Because in the end, most database migrations are very similar for SQL.
Yeah.
Just there's very there's a different flavor to each of them. So that's basically the implementation detail here. So let's see. Oops. Let's see. Here. Right. I am trying to rediscover the code because that changed a lot. Before the last time I looked into this was a long time ago. Yeah, here. This is what I was looking for. So we basically have all the render statements. So alter table, right? Table, right here, and this is the end result, right? Where we do all the heavy lifting first. So basically, before that, let's find out where this is called, so we can go through the code here. SQL render.
Probably Postgres renders.
Yeah, no, it's about finding the right chain right now, the right call chain to make it work. So right, and we have steps. This is what I'm trying to discover. We have steps. Render. Yeah. So this is the render script, right? So basically, in the end, what we do, we render like a migration file for you. To make things happen, right? So it's even now, just like being put on the spot and just trying to go through the code. It's fairly easy to find like certain puzzle pieces of the code base to make sense of the whole thing. Mm-hmm. And the main parts that we didn't look at that we do need to look at is just the models, basically the domain models. What does the Prisma migration engine use to determine what is going on? And at the core is usually always a migration, right? So we have a before and after, and then there's a lot of mappings going on to actually make it work, right? So every connector needs to determine what steps to take, distinct steps to make state A become state B. Let's say you add and delete a column. So it needs to figure out if you just renamed the column, for example, right? Or if you actually did remove or add a new column, because it is very hard if you don't have any context knowledge, right, of what is going on. So the migration engine really tries to figure out clever stuff for you. And it detects drift, right? So for that, we have to actually look into the database and determine what is the current schema. That is similar to what we do with introspection, right? We look into the database and determine the Prisma schema from it. And so I believe the thing that we're looking for is the SQL describer, database describer that powers the migration engine and mainly the introspection engine. So let's see if I can find the describer. Right. Maybe we even look at tests. That's maybe interesting.
Yep. Generally good stuff. I think a lot of us have seen how Git diffs often can mess up. Like it's technically correct, the diff, but it doesn't express your desire, as you say, but it somehow merges things together. It's the best they can do.
Yeah, it is really hard. Like usually tasks for humans, especially diffing, is much easier for a human than it is for a computer on unstructured data, which funny enough, code is unstructured data, more or less, right? So it is, all right, here we do some tests. Are these interesting? Yeah, basically it looks like this is a good place to start if you really want to understand what is going on in the migration engine. I don't think we have the time to really do that, but this is if you like, going through a test is one of my favorite things to discover a new code base. For sure. So I don't think this is very useful to like go through now.
Yeah, but that's at least we know where it is. We kind of know what it does. So once it gets state A to B, and from my personal experience, sometimes I try to do something, because I think, if I'm correct, this is also used when I do something like Prisma DB push, where I basically it tries to validate if whatever I try to push to the database does make sense. And sometimes when I do too much changes at once, it will prevent it. But if I do it piece by piece, so first remove something and then add it back under a different name, it'll magically work. And I think it's super hard to get this all right in general.
Yes, for sure. There's a lot, like we have a lot of engineering capacity on the migration engine, and it is a really hard problem to solve, for sure.
Yeah. Awesome. Thanks for the overview here as well.
Yeah.
I totally understand we're not going to go in detail.
Yeah.
I think the last thing I'd like to touch on is the Prisma data proxy, which is something that's been announced specifically for, I think, the main selling point, serverless functions.
Yes.
So if you could tell a little bit about it and maybe show some code or where it mixes in.
I actually cannot show code for that. That is under lock and key. That is not open source. That is our commercial side, right? But it totally makes sense to go back to what it means to have a binary, like a sidecar, and the Node API, right? So Prisma 3 now ships with the Node API, I said, and the data proxy, or why we still have the HTTP server around, is of course we need it for a remote data, like a remote engine, right? And so this is basically what the data proxy does. The data platform is what we call it right now. And basically, if you have a serverless function, Prisma doesn't actually help you at the moment when you just have the binary or the node library inside of your serverless function, right? So the main problem with serverless is connections to the database. There are databases that can deal with thousands of connections easily, and there are those that can't. And Postgres is one of those that doesn't scale well with a lot of connections. So usually what people do is use PG Bouncer to have a connection pool in front to not overload the database all the time. However, PG Bouncer has its tricks, that like specific things that you need to do, very specific semantics that you need to be aware of to make it work. But that's a solution that is proven. However, for other databases, it's not as easy, or it doesn't exist like a good solution right now. So what you can imagine. Yeah.
It kind of defies the thing of you wanted to avoid having servers to maintain, and now you have something you need to put in front of your database again, which brings you back.
Yes. So what the initial data platform will provide you is basically pushing the binary from your serverless function to our infrastructure, to a maintained server. And basically, because I told you under the hood is just HTTP with GraphQL, so it is basically transforming your stateful connections that you would need to maintain between the serverless function and the database, transforms it into HTTP calls, right? And that scales much better all of a sudden than just having to open a database connection for every single serverless function that you call, right? So that immediately eases the problem and actually allows you to scale out much more. Because you can just put more Prismas behind it, right? If you just imagine a simple structure, an infrastructure there.
Super interesting. Søren actually explained to me yesterday. I had an interview with him yesterday, and he explained this drive towards. And obviously, I directly thought back at Prisma 1, which kind of does this. And
exactly.
It's interesting how you managed to take forward the same idea, but in a much more ergonomic way, by not having to think about in local development, for instance, an extra machine. And if you deploy on Heroku for simple setup, you always need to think about the second one, and it's not obvious. But the idea is still the same, and the technology is still available there.
Yes.
Awesome. Yeah, I'm super excited to seeing that, and I think it also might help scaling apps in general, even if you're not serverless, just or have like one data access point. Right now, sometimes I want to split up my API into 2 APIs. I'd rather not connect them to the same database, but it's generally the first thing I start up with. And yeah, I really hope that this data proxy makes it easier.
Yes, for sure. Stay tuned. There will be news very soon about that.
Awesome. Dom, thanks so much for your time today. It was super interesting. Do you have anything to share, anything to plug, anything you want us to watch out for?
Well, first of all, thank you very much for having me. It was a pleasure. First time doing that, really. So you can reach out to us with questions on our public Slack, or if you have any questions to the code, where the team is happy to talk about it. It's open source, so we allow you to play with the code, make contributions if you want, but please talk to us before, because it is still a product that requires careful planning of API features. We cannot just add a ton of API calls, right? That needs to be planned by us. But anyways, we are hiring, as I said. We are super happy to find people in the TypeScript space that want to work more on the TypeScript side. We're happy to find Rust people, or as I said, anyone that wants to become good in Rust and wants to solve the issues that we have, because maybe something that we want to be better at the future is, of course, how performant the query engine works, how we do the query planning. And it's still a big contention point at the moment. We didn't go into detail there, but we chose a more inefficient approach for the sake of making the API powerful. But that doesn't mean that we should stay inefficient in some queries, right? Because a lot of people look at the generated SQL and say, oh, well, I could do this in one query, which is probably true, but it's very hard to optimize that with the stuff that we have at the moment, right? So we have a very flexible and powerful API, but now we also need to bring that to people that want a more performant ORM, right? So that is also a problem space where we want to design the core anew. And so if you're interested in working on that problem space, please reach out to us.
Awesome, great. Yeah, it's definitely an interesting project. It changed my life. It's really enabled me to do a lot of things that I could only dream of a few years back. And I'm super excited for the future of Prisma. Thanks again. Thanks everybody for watching, and I hope I'll see you around.
Thank you very much.
Bye.
Bye.